Good evening and welcome everybody to N Simplex Pachinko. This is Obi-Wan Pez. Sorry for that little deviation. Had the wrong scene selected for it. So. Alright. And I completely forgot to bring up the whiteboard before I started the stream, so yay. Alright. So we'll see if this actually starts up. Usually works on the second try. So, good evening, everyone. Tonight we are looking at Padé Approximants, and most likely Superbrain is back tonight, and maybe we'll, after we do Padé Approximants, maybe we'll get back into some of what we were talking about making an advancement in trying to figure out the magic square of squares problems. We might have a corollary going on. To be honest with you, I didn't do a whole lot of work on it. I did some, like, scribbling, but it was a bunch of dead ends and not terribly interesting. But, at any rate, we'll see how all this goes. So, I hope everybody's having a good week. Things have been going pretty well here. I had a flash of inspiration and contacted one of my friends and coworkers, and we might have an interesting side project going on at some point. Can't say much about it because, you know, haven't really done anything about it yet. And it'd be really cool if we could get it off the ground before I make any announcements. So, I'm going to work on something here to try and get some good values on a Desmos graph. Okay, let's do something like this. So, I wanted to thank Dr. Will Wood, who created the video on YouTube for Padé Approximants, and hey, yeah, me neither. But hey, we're working on it. That's the important part. Here we go. So I would like to get Dr. Wood's.
You guys listen. If you're thinking of going...
Nope. Oops. Stop. It just keeps wanting to autoplay. I swear it wouldn't. Anyway, so here is the video that is the inspiration for my study of this. And I mean, I've only done a week, 2 weeks of actual looking into this. Well, okay, 2 weeks of actually looking into this and trying to figure things out. It's really cool. Unfortunately, it isn't something that is really going to help like my calculus students. It's a really cool thing, and it's a really powerful tool for approximating a curve using something similar to a Taylor series. But the major problem is that you can't really do calculus on it. I mean, you can. It's not terribly difficult, but it would be rather inconvenient, especially to try to find integrals of things. It's the main thrust of all of this. Oh, using the wrong stylus. That doesn't work. So like I said, first got interested in this 2 weeks ago. So it's not like it's fresh in my mind, but it's not like it's might be a little much. Really? No. Okay. Express key settings. Not supported by this driver. That's cute. Oh man. Set for undo and redo. There we go. Okay. Let's try that again. So when we do this, we click the button. Yeah, cool. Okay. So for Padé Approximants, what we're going to do is start with a Taylor series. Still getting used to where everything is. I did bring home the new tablet this week because I just felt like it. My students were doing a bunch of stuff with, or they were doing an exam today, so like I didn't get to use it. And then I was like, I'll just take it home. So working with it today, and also trying to look at the software that Wacom put out with it that said like, hey, you have offers that you can try to use this software for, or you do a trial for this software. So I've tried out one of them so far, and it looks like it's an online only thing. I'm not too terribly wild about it, but I'm not gonna like bash anybody. So it looks like it's a good tool, but it's pretty much the same as Whiteboard, and it's online only. And yes, hashtag not sponsored. Just in case. All right, so we're going to start with a Taylor series approximation of whatever function we want, and then we're going to approximate the function with a better function called a Padé approximant, which is going to be represented by P mn of x, which is going to be a polynomial of degree m up top. So this is going to be like a sub 0 plus a sub 1x plus a sub 2x squared plus all the way out to a sub m x to the m. My students were just working with power series, so I thought that this would be appropriate to at least bring up to them. And so I said, okay, I'm going to need a few examples. So I pulled out, well, one of the examples Dr. Wood did was just like the sine of x. And he did a 2-2 Padé approximant, so a quadratic both top and bottom. And, it worked out pretty nicely. I wanted to do something that was a little more intensive, so I went with natural log of 1 plus x, which has more terms. Sines and cosines are only on alternating powers, so, and also hence why we call them even and odd functions. I mean, not the only reason, but certainly one of. Divided by b sub 0 plus b sub 1x plus b sub 2x squared, etc. All the way, nope, not a. All the way out to b sub n x to the n. So using polynomials of degrees m and n for the top and bottom, we can get all this stuff. It would also be worth our while to look at b0 here and say, well, if everything is 0 in the denominator, that's going to give us some problems. So we can assume that b0 is not going to be 0. So if we do this, we can in fact say that this is also going to be equivalent to taking b sub 0 and dividing it out from every term, or factoring it out from every term. So it's equivalent to say that we have a different constant, a sub 0 divided by b sub 0, which we can just call a sub 0. Because again, these are arbitrary constants until we say that they're not. Plus a sub 1x, etc. So the same thing that we got over on the previous section, a sub mx to the m. Now on the bottom, we call the b0 term can just now be 1. And so the denominator will always at least have a 1 in it. All other constants are going to be similarly divided by the former b sub 0, and they're just going to be potentially fractions. And I've found that the ones that I've done have also been fractions, so we were going to get them anyway, pretty much. So 1 plus b sub 1x plus etc. all the way out to b sub n x to the n. Again, just the same as we were doing. Okay, so for the functions we're looking at, you can kind of look at this and say, all right, we want a degree m over n rational function. This is what this is, right? A rational approximation for whatever function we want. If we want to do something like Dr. Wood had selected, f of x is equal to the sine of x, this is fine. I might suggest here that we use something that he originally chose a Padé 2 approximant and ended up with, I have it in my notes here. Padé 2, you know what, let's put that over here. Approximated by Padé 2 of x, which I'm just going to skip to the chase. If you want to watch the video, Super Brain you already have, so awesome, did your homework. We ended up getting x over 1 plus 1/6 x squared. Or this could end up being 6x over 6 plus x squared. All right, if we switch to my Desmos graph, let's see. I don't think I have anything. I hate doing this. There we go. Cool. So I'm going to put this one on hold for next. So if we do the sine of x, and then we do the Padé approximant of 6x divided by 6 plus x squared. Right, this at least gives us a reasonable approximation for stuff that's really close to, you know, -1 to 1. It's certainly no better, or sorry, certainly no worse than the Taylor approximation for this function out to degree 4. So this is something I didn't touch on yet, but the Taylor approximation out to degree 4 ends up just being x minus x to the third over 6. That is not what I wanted. X to the third over 6. Right, like I said, certainly no worse. All right, maybe a little worse. Yeah. All right. So okay, it's a little worse, but it's not bad. But here's the other thing, is that if we increase the degrees that we're going to use both Taylor and the Padé Approximants, the Padé Approximants eventually win out. They're going to eventually become more useful and more powerful. It's going to take probably at least 2 more terms. I haven't actually done the sign anywhere beyond 2-2. However, if we attempted to look at it at, let's say, a 4-4 approximant, and here's the other thing, the sine function oscillates around y equals 0. So I get the feeling that if we used a... Oh no, that's going to work itself out anyway. It's fine. I was going to say if we used a approximation that ended up naturally causing our function to have an asymptote at y equals 0, but then I realized that this one does, right? So this has our x up top and x squared down bottom, so this will naturally approach 0 as we go further out. So that's not necessarily a good hallmark of a function, but at the same time, like if we did something like sine of x over x, right, I think that this would probably end up being a good example to try to use a function that has a larger denominator. Because here this is going to go to 0. Now, since we specifically did that, I'm kind of curious. Right. So here, if we choose something like sine of x over x and use the Padé 2-2 to approximate the function, again, it gets a bit off. But at the same time, as we get further away, now it's starting to approach it better, which seems kind of ridiculous, but at the same time, you know, we'll get there. Again, if we did a Padé 4-4, I believe that this would show a much better convergence than the Taylor at degree 8. But again, I haven't done that one. Maybe I'll come back to that later. Okay, so I decided to go for a natural log of 1 plus x. And I said, okay, let's just do the same sort of thing. So let's do a Padé 2-2. And I'm going to go back to... right, back to the whiteboard. So if we say we want the natural log of 1 plus x to be approximated by a Taylor series, the first one... Did I really not do this? Huh, okay. I just skipped straight to the 4-4, so cool. We'll do a 2-2 by hand real quick, and then I'll show the 4-4. It gets a little out of hand, maybe, when we start getting into the bigger ones. But good news, it's something you can automate. Alright, so we want to approximate this with a, again, let's go Padé 2-2 approximant. And we're going to set this equal to... Okay, yeah, that's fine. The Taylor series, which I don't know if anybody else writes this, but of order 4. So I sort of started using this notation, not for any particular reason, but it was just convenient. That might be a horrible reason. So here, whenever we look at the Taylor series, to degree m plus n, and then we're going to set that equal to the Padé approximant. So for this one, natural log of 1 plus x, we're going to center the Taylor series at x equals 0. T subscript. Oh, Okay. That's also fair. Oh, superscript degree. I see. All right, we'll go with that. Technically, we need the 1 plus x. All right, so then here, if we use this, what we're going to do is say we've got a Padé approximant 2, 2, which is going to be a sub 0 plus a sub 1x plus a sub 2x squared divided by 1 plus b sub 1x plus b sub 2x squared, which is going to be set equal to the Taylor series for this particular function out to degree 4, which is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. The rest of everything else is going to be in a term which Dr. Wood calls O of x sub 5, which is just going to be like the overage or the remainder, or I'm not sure what O could be other than... I've seen it before, and it's not operation time. It's not computer science. But it just means that we're going over and beyond that. So we're not going to use anything of degree 5 or higher. So then what we do is we multiply and try to get the rational function to become just a polynomial. So a sub 0 plus a sub 1x plus a sub 2x squared is going to be equal to, here we get x minus x squared over 2 plus x, nope, x cubed over 3 minus x cubed, x to the 4th over 4 times 1 plus b sub 1x plus b sub 2x squared plus o at, or o of x to the 5th. So we're going to use an overage for x to the 5th. Anything that is x to the 5th or higher just gets absorbed. So then here we're going to multiply all this out. Right, is big O notation technically what this is? Because I would have thought, like, you know, again, this is just a remainder or an overage where we're just not calculating anything that's in there, like anything of that degree or higher. So, like I said, I have no idea if it actually is supposed to be big O notation, but okay. I'm not well versed in particularly big O notation, or as many people would notice, much higher level mathematics. It's one of the problems with being an undergraduate math education major and only intending to go to secondary level. Ah. Alright, left-hand side stays the same. Right-hand side, I ended up at one point just writing this out as table because I do like table notation, as perhaps silly as it may be. That's not what I want. X to the 1st, b sub 2x squared, x negative 1/2 x squared, 1/3 x cubed, fourth x to the fourth. All right, and for all, that's not supposed to happen. Apparently the black one is indicated as stuck on. Cool. All right, so for our x to the fifth and x to the sixth terms, these are just going to be ignored. And the rest of these terms can be added along diagonals. So, makes it nice. All right, this is going to be... Why, hello. Tony ZZ95, I think. Apologies, I can't actually see that. Let's figure it out over here. Yes, Tony ZZZ95. Thanks for the follow. Can't wait until I actually figure out the sounds on that thing. Get it correct. I was trying to sample the music from Square One TV, specifically the Mathman. It sounds like a coin-operated arcade machine, so I wanted to get that sound, but unfortunately my Audacity is playing up and I can't get it to work right. It's the weirdest thing. Anyway, thank you very much for the follow. Welcome in. If you have any questions on homework, then I would be very happy to help you try to answer any of those. If it is, again, much higher level mathematics than sophomore, junior level of college, I might be able to answer some of it, but can always give it a shot. But I may also refer you to Megalomorph or Taiyo Inouye, who are also excellent mathematical streamers at a bit higher level than I am. Okay, so for our initial term, we just get x. We also get here a plus parentheses b1 minus 1/2 x squared plus parentheses b2 minus 1/2 b1. Oh. No, that's right. Okay. Minus 1/2 b1 plus 1/3 x cubed plus parentheses a negative 1/2 b2 a plus 1/3 b1 and minus 1/4 all times x to the fourth. And again, everything else is big O of x to the fifth. All right, so then when we look at the individual terms that are here, we have to know that the left-hand side, a0, must match a constant on the right-hand side. There aren't any, so a sub 0 must therefore be equal to 0. A sub 1 must be equal to the coefficient of the x term on the right, which is 1. Very convenient. I think this is really the reason to get rid of b sub 0, because otherwise this is just equal to b sub 0 right here. And then a2 being our quadratic term, must match the quadratic term on the right, so b sub 1 minus a half. All right, and then the rest of them don't have any matching a's on the left, so these are all going to be zeros, equal to our cubic term, b sub 2 minus 1 half b sub 1 plus 1/3, and also 0 equals negative 1 half b sub 2 plus 1/3 b sub 1 minus 1/4. And you might notice that this is a 2x2 system of equations. So this is going to be a linearly independent solution of b1 and b2. At this point, it kind of has to be because we have completely different types of numbers here. So we got 1, negative 1 half, and 1/3. Here we have negative 1 half, 1/3, and negative 1/4. So it's not going to be a direct linearly dependent scalar multiplication from one to the next. Can't happen. So here we will get solutions. And the fact that our constants, our coefficients, are these particular numbers are pretty nice. And they're also well defined as far as that will happen. Depending on what function you're using, of course. It kind of all depends. But they end up with this nice diagonal pattern. So I don't think it necessarily has to happen like exactly like this, because it could... Okay. Yeah, because in theory we could be using a Taylor approximation that has factorials in the denominator. So yeah, okay, it's not going to happen like that all the time, but at least for the natural log function, it's going to be nice. Curses. Sometimes the mouth is working faster than the brain, right? But if we move these over and make it a little bit nicer, this is going to get us a 1 half b1 minus b2 is equal to 1/3, and a, let's just move everything. So negative 1/3 b1 plus a 1 half b2 is equal to negative 1/4. If we multiply the entire denominator by, or not denominator, if we multiply the second equation by 2 and then add, we're going to get a 1 half minus 2/3, which is 3/6 minus 4/6 is going to be negative 1/6 b1. Twice 1 half b2 is going to be a positive b2 plus a negative b2 is going to be gone, is equal to, here we have a negative 1 half plus 1/3. So again, 6 is going to be 2/6 minus 3/6 is going to be a negative 1/6. So b1 is 1. Using the first equation, we have a 1 half here, and we can subtract it from both sides. That's going to get us a 1/3 minus a half is again going to be negative 1/6, and then that is a switch sign. So b2 is going to be a positive 1. Check me on this. All right, then we come back here, and a2 is going to be equal to a 1 minus a half, so a2 is going to be just a half. Yeah, 1 half minus 1/3 if you go the other way. So yeah, 3/6 minus 2/6. Okay, cool. So this means that the Padé approximant 2 for the natural log of 1 plus x is going to be approximated by, again, Padé 2 of x is equal to, this is a bad idea. Don't put it here. Can put it right there. That's fine. Is going to be equal to, all right, a sub 0 is 0, so that's gone. A sub 1 is 1, so that's x. A sub 2 is 1 half, so this is a plus 1 half x squared. Divided by, b sub 0 was, again, 1, just let it be 1, plus b sub 1 was 1, so that's x, plus b sub 2 is 1, so that's x squared. Alright, and then if we go to browser window, alright, we have natural log of 1 plus x, and then if we do, again, Padé approximant of x plus 1 half x squared over 1 plus x squared. That wasn't anticlimactic. Yeah, okay. This again at least works in the immediate vicinity surrounding x equals 0. Again, sort of underwhelming in terms of the same-sized Taylor polynomial. Again, this is going out to x to the 4th. So this was going to be x minus x squared over 2. Yeah, this is better. Plus x to the 3rd over 3 minus x to the 4th over 4. Yeah, okay. So one of my students certainly would be asking, why are we doing this if it's worse? The answer is, okay, hold on. Let's try and go at a higher degree. So I'm not terribly well versed in this, but I imagine that this is just because we have a like 4th degree Taylor polynomial. It has multiple terms going out. Whereas this is just going to be a quadratic both top and bottom, so like I don't know if there's something with, like, statistically speaking, if there's something with degrees of freedom or whatever that's messing with it. I'd like to know more, but I'm not the person to ask, I don't think. So here's the thing. We did do I did do on the side a 4-4 Padé approximant, which is, again, calculated the same as this, but has many more terms. So if we want the Padé 4-4 of x for this thing, this is going to be, again, a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the 4th, all divided by 1 plus b sub 1x plus b sub 2x squared plus b sub 3x cubed plus b sub 4x to the 4th. Okay, and we're going to, again, set this equal to the Taylor approximation going out to 8, or degree 8. So x minus x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6 plus x to the 7th over 7 minus x to the 8th over 8 plus big O of x to the ninth. All right, all of our overage terms in there. So then if we multiply all this out, I will spare you the individual minutia for all this. It can be left to as an exercise for the reader. All right, what we eventually come out with is that we have a sub 0 is going to be equal to 0, again, because there is no constant on the right-hand side. Easy enough. All right, the natural log Taylor expansion has no constant term, so therefore that's why that happens. Although, a lot of other functions in Taylor form do, and so that constant will be reflected directly with a sub 0. Okay. A sub 1 is going to be equal to 1. A sub 2 is going to be equal to b sub 1 minus a half. So, again, so far, suspiciously familiar. It shouldn't really be surprising, right? Because the lower terms don't have the involvement of any of these upper terms that we skipped on the one above. So, yeah, okay. Everything out to x to the third, everything out to x to the fourth should be identical. All right, so a sub 3 is equal to b sub 2 minus 1 half b sub 1 plus 1/3, right? Yeah. A sub 4 is equal to 1/3 b sub 1 minus 1 half b sub 2 plus b sub 3. I reversed the order of these. Why did I do that? Yeah, the y-intercept, yep. All right, minus 1/4. Yeah, I shouldn't have done that. Let's just rewrite it. Trying to be cute over here or something, I don't know. All right, so that's b sub 3 minus 1 half b sub 2 plus b sub 1, 1/3 b sub 1 minus 1/4. All right, then we're out of a terms, so then we move on to the b terms, which are going to be 0 equals. Again, start with the... that's why I put them in order. Okay. So I flipped them in reverse order because I wanted to show the basically row reduced echelon form, the matrix version, so that you start with B1, B2, B3, B4, just going across. It doesn't really matter, but anyway, this is going to be 0 equals a negative 1/4 B1 plus 1/3 B2 minus 1/2 B1 plus 1/5. That's not what I wanted. Man. Just all sorts of distracted. That's fine. 1, 2, that's 3. Alright, plus b sub 4 plus 1/5. Yeah. 0 equals a 1/5 b1 minus 1/4 b2 plus 1/3 b3 minus 1/2 b4 minus 1/6 a A0 equals negative 1/6 B1 plus 1/5 B2 minus 1/4 B3 plus 1/3 B4 plus 1/7. The Taken Cup. Hello. How are you? So, good evening. My name is Obi-Wan Pez. This is N Simplex Pachinko. I am a math streamer for the most part, and I like to help people with their mathematical type problems. If you have anything that you would be interested in learning at a deeper level, please let me know, and I will attempt to help you out. And you can totally interrupt me for this, because this is just me presenting something. Alrighty. So, the Taking Cup. How far have you gotten in your mathematical learning slash career? This is, um, this is a new thing for me. So I'm trying to figure this out. I have this done in my notes. It's not terribly difficult. Like an Algebra 2 student an Algebra 2 student could solve this part. The stuff at the beginning takes a little bit of work, but yes, it is tedious. All right, so I plugged this system of equations into a calculator because I don't want to do that by hand. And basically, yes. Let the calculator do the heavy lifting, so to speak. So basically, what I did was I said, okay, we're going to get all of our 1, 2, 3, 4, 1, 2, 3, 4. We're going to find A0, A1, A2, A3, A4, B1, B2, B3, and B4. Right, this is a matter of simple linear algebra at this point. If linear algebra is not simple yet, don't worry. You say simple. Again, this part of linear algebra especially is let the computer do the work. And so it doesn't actually end up being terribly difficult, but at the same time, takes a little bit of getting used to. And especially, it's very annoying when you have to do it by hand. All right, so, actually, right, I actually did want this to be the other way around first. Because we do technically want to show the equation for a sub 0, which is just going to be a sub 0 plus a bunch of zeros is equal to 0. Hooray. A little boring, but whatever, it's fine. All right, the equation concerning A1 is that A1 is equal to 1. A2 minus a B1. That's not it. That's A4. And now it's A3. All right, hang on. 0, 1, 2, 3, 4, 1. Okay, there we go. That is our B1. So it has a coefficient of -1 when we shift this over, which has then nice. What level? A is equal to a negative 1/2 on the other side. And then the rest of these just get zeros. Okay, A3. That's not it. That one's A3. Is equal to a, if we shift the b's to the opposite side. No, we don't. Yes, sorry. Move the b's with the a's. We get a 1/2 b1 and a negative 1 b2 with a couple of zeros here. Set equal to a 1/3. Okay, we got a4. This is 0, 1, 2, 3, 4. And we get a negative 1/3 b1, a positive 1/2 b2, a negative 1 b3, and a... Very nice. How are you liking Common Core? And a negative 1/4 for a constant. I kid. I know a lot of people have some issues with it. Being somebody who... I do want your opinion, but being somebody who is not teaching in a high school anymore and seeing all of this happen, it's very fascinating. And now I've got kids of my own who are starting in, my daughter's in 4th grade math, and so she's starting to learn, like, you know, mostly like larger multiplication and division. And the fact that she's doing, like, she's a little upset about Common Core. Like, I don't understand. Then when the teacher asks her what she doesn't understand, she's like, just gonna shut my mouth now. I'm like, no. you gotta come up with the... But we're getting there. All right. So the rest of this stuff, right? This is going to be 1/5, negative 1/6, 1/7, and negative 1/8. They're going to be in these slots. This one's 1/5, 1/6, 1/7, 1/8. I'll make sure I align those roughly. All right, so B1 is going to be... Oh, right. These all have to be opposite because they need to be taken to the other side. Might as well do it for all the other ones, too. All the B's here. All going to be moved over to the opposite side. So that's going to negate all the signs. Yeah. I mean, one of the biggest problems that I hear is all the parents complaining about it, like, I don't understand this. It's not the same as what we learned when we were kids. And I was like, no, it's not. And that's intentional. So I finally, like, got to sit down and, like, study some of the Common Core stuff. And finally, I was like, ah, now I definitely get it. And so I am trying to work with a couple of parents, especially in our area. Just like, okay, here's what you don't understand. It's an interesting process. But the whole idea being that Common Core is supposed to teach algebraic principles even at 1st grade. And the operations that you learn, addition, subtraction, multiplication, division, are not to be divorced from algebraic thinking, which is kind of how we all learned it, all of us old folks. Um, the way that we learned how to do these operations, it's very isolated from the rest of mathematics. You don't really learn about like how this is all interconnected until you start doing algebra, and then it's like, a bunch of my classmates were like, I don't get this because it's so different. We're throwing in letters and everything's completely changed. And I was sitting there, much like you probably were, like, no, not really. Like, everything's kind of the same. -1/5 and 1/4. Okay. So solving what are called simultaneous equations or systems of equations like this, again, get really tedious really quickly when you've got large sets of data or many different equations, especially with many different variables. In this case, we have a total of 9 variables. Now, granted, one of them is 0, one of them is just 1, so we didn't actually have to write those. But for completeness, generally speaking, I do it anyway, just to be annoying. What the calculator is going to do is it will solve these equations in here. Thank you for the follow, the Taking Cup. I hope to be a source of enjoyment and education throughout the years. So we'll see how it goes. Basically what the calculator does is it takes these 4 equations down here, which again correspond with these 4 equations here. And it starts saying like, okay, let's do what I did up here. Now you may not quite skip right over it. You may not quite understand it yet, and that's perfectly fine. Don't worry about it. But we moved all of the b's from these equations here to the left-hand side, just like we did with the 4x4 system of equations. This is a 2x2 system of equations. And by adding equations together, this is a style of solving systems of equations that has its roots back to ancient China. So in China, they would have weights, scales. So pan balances. You'd put weights on either side and then try to balance it out. And then the merchants would be able to figure out how much you owed based on, what got put on both sides. So you'd pay by weight. So the old adages or the old problems, the classic problems that exist were kind of like, okay, if you got three peaches and 2 plums, and it weighs this much or costs this much or whatever you want to use, and if you have 4 peaches and 3 plums and it costs this much, then how much is the cost of each individual peach and plum? So you can solve that using these simultaneous equations. Basically, again, we're going to either add or subtract the 2 equations together. With the fish is entirely different. You need more information. Also depends on how fresh it is. Yesterday's fish goes quick. All right, so then here we ended up adding 2 of the lower equation to the upper equation. And here, if we add 2 halves to a -1 of b2, that becomes 0. So they go away. That's now gone. And I don't usually write +0 in these particular cases, but, it's good as a placeholder. And then on the left-hand side, we say, okay, we're subtracting 2/3. If we multiply this 2 into that, we're subtracting 2/3 from 1/2 of the b1s. So that ends up getting us a -1/6. If you add the fractions or subtract the fractions. And then on the right-hand side, this is a 1/3 minus 2/4 or minus a half. So again, negative 1/6. So if we've got negative 1/6 of b1 is equal to negative 1/6, okay, b1 is just 1. And then again, we did the same thing. We can take b1 and now just plug it back into this equation up here and say 1/2 minus b2 is equal to 1/3. And then subtract the half from both sides. It's 1/3 minus a half. We already did that. It's negative 1/6 is equal to negative b2. Did I mess that up? I did. Oh, Superbrain, you didn't catch me. Maybe that's why it got screwed up. Maybe that's why it looks so bad. All right, let's try this again. Hang on. b2. So that is the x term. No, it's the x squared term. All right, 1/6. Hey, there we go. I knew it looked wrong. All right, what do you think? No, that's fine. So yeah, this looks way better than the Taylor approximation. Oh man, Dr. Wood is going to be like, I'm messing up the method the whole way. Anyway, so it's the black one right here. So going in the positive direction, it's way more accurate than Taylor. Oh, I'm sorry. Maybe like I could turn on the plot. There you go. So yeah, it's this black one here. Oops. No, I hit Excel. Which in the negative direction, right, starts going off to negative infinity at roughly the same place that the natural log does. Unlike the polynomial, which goes off to negative infinity at kind of a slow rate, right? It's a quadratic. So then this is going to pass through the asymptote. But the black series has a 0 in the denominator, which means it has an asymptote. I guess we could figure out what the actual 0 is there. Sure, why not? Oh, we'll just copy the bottom, paste it over here. This is the lazy man's version. All right, so where's the 0 here? This is negative 1.268, whatever that is. So this value here is going to be our vertical asymptote, which is, again, slightly off from the natural log, which is -1, but, you know, it has an asymptote, unlike the polynomial, which doesn't. So, yeah, in the United States, not really. In my classroom specifically, I give my students the pep talk at the beginning of the semester, where solving it algebraically is going to be basically the gold standard. Solving something graphically is a fallback position that you should not do unless it's actually impossible or incredibly tedious, like, you know, trying to do a 4/4 Padé approximant, because who would do that? So we don't technically think of it quite as valid, if you will, unless it's something you have to do. Anyway, hang on one sec. I'm going to come back. Okay. Right. No, no, no. I mean, like when I'm doing stuff just on the side, of course I'll do that. Especially if I'm just trying to find like an approximation like this, I don't really care what that value. I don't really care necessarily what that value is exactly. I'll figure it out later maybe because I know I can solve a quadratic. That's easy enough. But yeah, for illustration purposes, I'm not gonna ding anybody for yeah for illustration purposes. I'm not gonna ding anybody for uh, doing this graphically. That's fine. Whatever. It's a value that is negative and fairly close to -1, so yeah, it works. It also has, again, a vertical asymptote at -4.7, but we don't care about any of that because that's out of the domain of our natural log function. So, but anyway, um, yeah, so much better. Whew. All right. See, this is the problem with not actually doing the example out ahead of time. I've done the 4-4. I haven't done the 2-2. So, or literally now I have. Yeah. So here we get at least a reasonable approximation for these values. So we'll call it good enough for the 2-2 Padé approximant versus the actual function, natural log of 1 plus x. And again, it works much better in both directions. So I'm not sure exactly about being much closer, but yeah, there we go. So blue deviates first. That's the Taylor series. I'm pretty sure it holds for the rest of it too. It must, right? The way I want it. Goodness. But either way, also, I have to go really far before it actually deviates. So, both of them are very good within the local region. It's just that the Padé approximant is much closer for much longer. Okay. So now we go and look at the rest of the 4-4 here. Let's drop that. And, well, yeah, but here's the thing, right? If you're willing to do, and it's not really that much more work, right? It's a matter of finding a way to make the script work. Because I could probably do this in MATLAB, take a couple hours to figure it out and debug it. But yeah, I think I could do this in MATLAB. I'm going to get myself in trouble by saying that, but okay. Because now somebody's going to challenge me. Okay. So based on this, we can get a identity matrix that's going to multiply by our I prefer Scilab technically, but that's just because I'm kind of a snob about that and it's free. MATLAB itself is actually, pretty decent in terms of being able to do stuff, but at the same time, there are certain aspects of it that sort of bug me. I can't think of any offhand now. But all right, so A3, A4. Identity matrix times all this stuff is just going to say, all right, we're just going to get these numbers themselves. All right, is equal to, so say 0, 1, no, jeez. Well, okay, those two are correct. All right, we got a 0, 1. Then the next ones are going to be, oops, there we go. A2 is, oh, come on, 3 halves. A3 is 13/21, and A4 is 5/84. B1 is 2, B2 is 9/7, B3 is 2/7, and B4 is 1/70. And again, if we multiply by like B0, again, if we let it not be 1, then we could clean up all of the fractions by multiplying by the least common multiple of all the denominators. So we'd end up with just two integer coefficient polynomials, top and bottom. But at any rate, so this ends up making it that the Padé 4/4 approximant of the Taylor series, or sorry, of the natural log of 1 plus x is approximated by this thing. Again, a0 is 0, a1 is 1, so that's x, plus 3/2 x squared, plus 13/21 x cubed, plus 5/84 x to the 4th. Yeah. 1 plus 2x plus 9/7 x squared plus 2/7 x cubed plus 1/70 x to the 4th. All right, and then if we take this thing and go back to the Desmos graph, okay, it's going to get divided by x plus 3/2 x squared, 5/84 x to the 4th, divided by 1 plus 2x plus 9/7 x squared. Absolutely taken cup. I will get to you just as soon as I plug this in. Over 70 x to 4. Right. So again, as we're going down with the asymptote here, it's actually much closer again. We do have 4 zeros, so there are going to be 4 asymptotes. But again, it's the other 3 are prior to this last one. And yeah, it turns out that it's not like that much better unless you look really close or like within the first, what is that, 3? Yeah. Like within 3, it's practically sitting on top of the 2/2 Padé approximant. So like, oh wait, no, that's the 2/2. Okay. Jeez. It's practically sitting on top of the function, right? So whether it's the green value here or the red value here, we've got pretty much the same thing. Up to E, nice. Go figure. And then yeah, when it's still much better, even out to 4, 5, and all the way here at 8, right? At the value of 8. Oh, you meant the y value of E. Maybe. Is that what you meant? At 8, we've got a 2.1861 versus a 2.1972. So, like, that's pretty good. So, if we actually... g of x is equal to this, and f of x is equal to this, we can actually figure out right? We could actually do the nice easy stuff here. F at 8 minus G at 8, oops, 8, divided by F at 8. So this is a 0.5% error. And I think most of the time we're usually trained, at least in the United States, to count anything up to 2 as being good enough. So 2% error is usually considered good. Okay, so the taking cup. Stuck on a part, but I think I'm going to do it in the morning. Oh, okay. That's also fair. If you want to drop that in the chat window here, I could mark that. It is timestamp. See, where are we so far? We are at 1 hour 30 minutes. So if you want to ask your question here, the video on demand will be available tomorrow morning, and you can scroll ahead to 90 minutes and get at least an answer. May not be a super good one, but no. It's fine. All right, and then if we want to do like, where is this going to be? I don't think we can do something like this. This would be crazy, right? Yeah, we could do this because this is its own function. Nice. Awesome. Okay, so we can figure out where that 2% error will come, right? That's going to be about y equals 0.02. There you go, right around 15. So, you know, we've got something that in the United States at least is good enough up until x equals 15. Yeah, so my it's just ingrained into our heads really that this is what you do. So yeah, like I said, Padé 4 approximants really good up until x equals 15. This is way farther than the Taylor series. Taylor series can only get out to, let's call that h of x, and then do the same, right? So where does h of x meet this? Hang on. No, that's not. Well, something's not right. You see what I'm saying? If we take the original function f, and we're trying to find the distance between f and h, and then we divide by f, value of f, we should be getting something approaching. What did I do? How do I make a circle? Generally speaking, I grin and bear it. So I teach trigonometry, and it's that's not what I want to do. I teach trigonometry for the most part, and it's a struggle. If I want to do a circle on, like, generally speaking, I'm going to do it on Paint or Zoom or one of these other ones that has like a preset to be able to do an ellipse of some sort, and then just get something that's pretty close. If I'm going to do it on something like this, just freehand it, it gets a little rough. So my favorite is start with your center and know how large you want this thing to be. So I'm just going to do one that's two squares around. Now I am cheating because I am using graph paper, or rather, I'm doing something really useful here. All right, and by the ways of trigonometry, I do know some special values around the circle. So you could freehand this and just say this is going to be almost vertical. I mean, literally, it's vertical at these side points, and it's going to be horizontal at the top and the bottom. But it stays horizontal and vertical for no time at all. So you just sort of approximate it like this and go out. You should be at a diagonal, 45 degrees, at the 45-degree angle that's coming out this way. So this angle here is going to be 45 degrees when this angle here is at 45 degrees as well. So that's also another way to show that you've gone either too far or not far enough, is to say if you're like way out here and still kind of flat at this 45-degree angle, you didn't go far enough, right? You didn't go up fast enough. And I use the artist method, which is when you're doing stuff on like sketches, generally you just draw a bunch of little lines and connect them. So this is again going to go like this. Oh. And then we use the undo button. Nope. Going backwards, I'm having some issues. It's alright, this circle is going to have a goiter. So this is not awful, but it's not great. If you're just trying to draw like a quick circle, practice. This is not good, but it'll do in a pinch. Especially if I'm just going to draw a quick unit circle like this and be like, I want this angle here. Theta. There you go. What's this angle theta? And then, you know, my students and I can work off of this. So, generally speaking, I'm going to do an artist method when I have time, and I'm going to just sketch one real quick when I don't. With this, there's also a couple of special values, like I said. There is, if you go halfway up your radius, you are going to reach the end of your circle at a 30-degree angle. So like a third of the way here is going to get you a distance of 1/2. You should be able to trace that, and again, if you're actually doing it as a straight line. When you go 3/4 the way up, your 45-degree angle should be just under that. And then similarly, when you have a 60-degree angle, you're going to go halfway across your radius here. That worked. Okay. Jeez. The place where it hits the circle should be, again, roughly here. So this is too tall. That's way, way too tall. There we go. That's better. So it should be here. So like I said, it's really just kind of a matter of practice. If you have the time to place down more points where you know that they're going to be, like based on a circle, then you're going to be more accurate. I mean, it's the same as with any graph, right? If you graph something like this and you want the curve that goes through those points, it's going to be kind of rough. And besides that, there's more than one. right? I even missed that one. But if you've got more points, then you'll be able to hit the curve in more places much more easily. There we go. That was not a quick answer to a quick question, but I hope it at least helps. One of the other things you can do, if you want those values, the actual values, you can plug in on your calculator an equation of a circle. The equation of a circle can be based on 3 pieces of information and the Pythagorean theorem. You have a right triangle. This is your x distance to this point x comma y. This is your y distance, and this is the radius of the circle. So that's the equation. If you want to plug it into your calculator, typically TI calculators are going to require you to put this in y equals format. So if you want to know where these are, you have to solve for y. So bump that. This is going to be r squared minus x squared. And then we took the square root in order to undo the square. So this is going to get you the top half of the semicircle. And why that is, we can discuss on another day. But anytime you just want like some numbers that go in a circle, you can use that. It also helps that the circle is 100% symmetric. So if you have a value that is here, you also have a mirrored value of that exact same point down here and over here and up here. Nope. Oh, should have been here. Oh well. So again, practical upshot of that is if you have a table of values that get you x and y points, all you're going to have to do is negate one or the other or both, and you're going to get all the mirrored points in the circle for that particular point. Hope it helps. Might not, if I'm honest. But at the very least, it'll get you some deeper understanding of what's going on in all of this stuff. And definitely, if you're at all interested, come on back and ask some questions. I only stream math on Wednesday nights, but I do also stream gaming on Friday nights. And if you ask a math question then, or if you send an email to my channel name at gmail.com, so nsimplexpachinko@gmail.com. Generally speaking, I will take a look at them and get back to you the next Wednesday. Or, again, if it's something quick that I can do just off the top of my head, then I can do it while I'm gaming on Friday nights. Or I can say I'll give you a much more detailed explanation next week. Oh. Oh, yeah, actually, right. That's not awful, right? 3-4 Padé, huh? We're gonna go back to this, aren't we? No, that's not theta. X. Yeah, because if we do a Taylor for, oh man, arctan arctan's gonna be nasty though, right? I mean, of course you're trying to move me in that direction. Man, I haven't even finished my coffee. It's almost 11. Woo! No, I'm certainly going to be staying up for whatever raid stream we end up doing after this. Oh no, that's going to be weird. Right, what's the arctangent? How'd you get that? I don't doubt you. Oh, okay. Wolfram. Just ask what's the Taylor series of sine of 4 arctangent. I mean, it's not like it matters either way, right? It's as long as it got you something reasonable. Oh, so did you... Oh, that's an interesting one, right? So if you... No, that's not what I want. That's what I want. So to do this one, y is approximately... Nope. Y is approximately equal to a plus b x squared. Oh, that doesn't work. Never mind. F? I wonder if this works. I haven't actually tried it. Probably not. No. It's gonna yell at me. No. 13. Oh, that's weird. We do a table. Whatever. Do like 0, 0. No. X 1 y 1. Alright, so then we do 1 ln 2 2 ln 3 4 It's not graphing it. It's gonna just, yeah. Why? 1. Yeah. Right, differentiating is not difficult. It certainly did a thing. So yeah, the next question is it the same as the, that's not the Taylor series. Is it going to be the same as the Taylor series of what we got before? I mean, it should be, right? Well, actually it isn't, because, yeah, never mind. It's more accurate within the local region. Well, I can't say that. It's more accurate further away than the Taylor series was. Hmm. Yeah. I think it might be further away as we get down toward the negative region. Anyway, I've got too much stuff going on here. I'm really suspicious of this thing. Because this was supposed to be, right, when is the Taylor series approximation for our natural log out to 2, yeah, degree 2. When is that going to be within 2% of this value? And the thing is that it didn't have an intersection. So that means it never is within 2%. But like they're they're really close in here. So I feel like I mean, I guess it's possible that they never reach between, or they never reach 2%, but it just feels wrong. I don't know. It's like 2.5, 1.238, 1.25. Okay. That's the other one. Yeah, where's this? Oh, wait a minute. No. That's not what I was looking for. Oh. Yes, thank you. It's definitely not the Taylor series. uh, yeah, thanks. That's it is never within 2%. Hey, that's fine. It's that was not necessarily something you should have been required to get. All right, so then we want this. X minus x squared over 2. There we go. No. Plus x to the third over 3 minus x to the fourth over 4. All right. So we wanted purple and black, which is here. Right. So we get outside of that point, outside of that 2% at 0.58. Whereas our other one went to 15, and it again was centered at a Taylor series approximation at 0. So like that is just absurd. in terms of the difference between these two series. Okay, let's just get rid of this stuff because man, good times though. Where am I? I'm at home. Anyway, get rid of this. Let's look at. So I had another thought, which I don't want to do that. I had another thought at one point, which was, what about a 5-3 approximant? Because this, in theory, would have a linear asymptote, right? It has a slant asymptote, which I was thinking if our natural log is doing something like this, then a Taylor approximant, which had like a linear asymptote could, in theory, have a better reach, right? Like this could get further out. Potentially, could get further out. What I didn't anticipate was that, oh right, this is not going to be linear because this is 5-3. So yeah, exactly. This one has an x squared asymptote. And as it turns out, the best way to approximate it is to end up with a negative asymptote that way. So I was like, wow, that's not even close. So what I should have done was do a 5-4 or maybe a 6-5. 4-3 potentially even. Although 4-3 would probably end up not quite as good as 4-4. Just gonna go out on a limb here, because then I think you could in fact encompass the I think it would encompass the 5-4. Sorry, the 4-3 would encompass the no, other way. The 4-4 would encompass the 4-3, because if the 4-3 were better than the 4-4, then the asymptote, the quadratic term, nope, the quartic term in the denominator would just be 0, right? If it were better without it. Then it would just get rid of it. So I think that this is one of the reasons they keep an equal number in both top and bottom. Is just because it works out nicer. So this still ended up with a the 5-3, and still ended up with some good stuff in here. We ended up with the ridiculous 2, 3, 4, 5, 6, 4, 5, 6, 7. 1, 0, 0, 0, -1, 0, 0. All right, and then So this one ends up with a bunch of stuff in it. Oh, did I? Yeah, I dropped a 0 for this because it was going to be 0 again. So 0, 0, 1, 0, 0, a half, -1, 0. And we get the same pattern that we did in the above one, where we're just going to, again, increase all of our values. These end up being like diagonal. 1/2, -1/3, so 1/2, -1/3, +1/4, -1/3, +1/4, -1/5, 1/4, -1/5, +1/6, and this was 1, 2, 3, 4, 5, 6, 8, 1, 2, 3, 4, 5, 6, 7, 8, -1/5, 1/6, -1/7. Right, and everything else is zeros except here. Damn, I forgot something. Nothing in terms of what we're doing here. I forgot that it is December 1st. And I have an advent calendar waiting for me too. Although in my case, mine is our friend decided to put this together a number of years ago, and I've been participating ever since. Ours is a beer advent calendar. So I should probably break it out, but alright, so then our constants over here, we're at 1, -1/2, +1/3, -1/4, etc. Up to -1/8 down the bottom. Forgive me. Alright, so then this ends up with 1, 2, 3, A, 4, A, 5. It's fine. Alright, this was equal to A1 was 1. A2 was 11/8. A3 was 157 over 336. And A4 is 1 over 56. A5 is a -1 over 1,120. B1 was a 15/8. B2 was a 15/14. And B3 was a 5/28. So then, go back here. Let's copy this one because it's almost the same, barring the numbers. At least the structure is the same. GH. All right, so we got a 1. This one's going to be 11 over 8. This one's going to be 157 over 36. This is a 1 over 56. Minus 1 over 1120 x to the 5th. All right, on the bottom, x to the 3rd is 5/28. X squared is 15/14. Again, it's already taking shape. It's pretty nice. And 2 is a 15 over 8. So again, it looks pretty decent, but it's certainly, this one is not going to be any better than the 4/4. Or at least, well, I guess it could be in theory better than the 4/4 in some places. I haven't actually done any analysis on this, so, well, let's find out. Yeah, okay, so purple's a little worse than green. But again, overall, it's not too bad. If we, why did I get rid of that? F of x here. I redefined h too many times. J. F of x minus j of x. The absolute value over j of x is that. And then we go with a y equals 0.02 equals. Apparently wrong button. Right, we're going to go out to 8.05. So about half the distance as the 4/4 approximant. So I mean, it's possible. I got a search up here somewhere, right? No. Global math art contest. That could be interesting. Submit this grad. No. Yeah, students anyway. No, that's not going to be it. Restrictions, regressions, sliders. No. Not particularly. Doesn't look like it. Oh, they could do the circles within circles, whatever the epicycle art. I forget what that's all called. I mean, you can do a Fourier series, but who is it? Numberphile did something with it. They were trying to draw various. They're trying to draw various pictures, and they said like literally you can turn any sort of line art into one of these functions. I don't know if it was. Yeah, it must have been Fourier, because you're taking like radius 1, radius 2, radius 3, etc. as far as you need to go, right? That sounds right. It's been a long time since I've done Fourier series. Yeah. Anyway, we can get rid of this. See, our 5.3 Padé is not as good as the 4.4. So, might be something interesting in that just by itself. 5.4, I suppose, might be interesting. Again, I haven't done any of this, but might be worth like some quick investigation. Alrighty. Whee. I know a couple weeks ago I had mentioned doing a thing on Lagrange? Yeah, Lagrange interpolation. I haven't really come up with anything interesting on that, but it was just basically like if you have a series of points, and actually Dr. Wood's channel did something on that too. Basically, you can find the Lagrange interpolation of this particular set of points by finding the sum of, or 1 to n, I guess, of all data point y's sub I times Lagrange the Lagrange polynomial for each of the individual sets. So basically what we do is we exclude any one of the points and use its y value. And then the L sub I is just a polynomial formed by the product of it gets really, it gets a little funky. It's fine. Yeah, no, that's fine. No, J goes from 1 to n, where J is not equal to I. So you take basically one of these things and pick this point here, and then you multiply all of the others together as linear factors. And you say that the function is going to have a 0 value at every single one of these points because you just constructed it that way. So it was going to be x minus x sub j, right, the product of these, divided by x minus, wait, hang on, x sub I minus x sub j. Yeah, okay. So if this was like, 1, 3, and then the rest of these were all nice values. Say like the Lagrange 1 is going to be x minus, so like x equals 2, x equals 3. Ugh, God, these are close. X minus 3, x minus 3.2, x minus 4, x minus 5, and then multiply all these together and then divide by what you get at x equals 1. So then 1 minus 2, 1 minus 3, 1 minus 3.2, 1 minus 4, 1 minus 5. And then the y value you take is just 3. So then this is all 1, right? This is all 1 at x equals 1. Because you just divided by all the values that you just plugged in. And then let y sub 1 be 3. So then it's just going to be 3 times 1. It's going to be 3 at this value. And then at every single other point, it's 0. And then you do the same for the second point. And then the same for the third point, the fourth point, fifth point, sixth point, all the way through your whole data set, doing the exact same thing, and then sum all of them up. So I hadn't really come up with, like, again, a solution for it, but I thought it was interesting. Anyway. Whew. I mean, it's something you maybe should know, but I don't know. It makes trying to find a polynomial of best fit like trivial, essentially. But your polynomial is always going to be 1 degree higher than the number of data points. No, sorry, 1 degree lower than the number of data points. Yeah, and I mean, it's, again, like I said, it's practically trivial. This one's again on Dr. Wood's channel, so we'll shout that out once more. Yeah, that one. So anyway, that's the, oh no, that's Padé Approximants. Lagrange interpolation is that one. Whoa. Huh. I mean, it's very possible you know it, just you've already seen the other one, so if you're anything like me, it's like, oh, let's watch all the rest of them on this channel. You know, I think he's using, well, he's using a whiteboard that uses a marker style pen. Oh, right, yeah. Because I literally did that earlier. Okay. So I think he might actually use one of the software packages I was looking at earlier. I don't know. I still like this whiteboard. Shocking. This is why I have multiple accounts. I gotta stop watching gaming videos from my one of my other accounts though. Usually useful, yeah. All right, I think that is gonna about wrap it up for us for tonight. So, thank you very much, Superbrain, for coming on in. Thank you to the Taking Cup, and also thank you to was it Jeff? Nope, Tony. Man, Tony ZZZ95 and the Taking Cup. Thank you so much for coming in, and hope to see you again. We'll okay, yeah, that sounds good. I will be looking out for your email. And hopefully I'll get some more work done over the next week on your problem that you share with me. So try to get some extra stuff done on that. Alrighty, so let's raid out. Let's do oh, probably Jason Charles Miller again. So oh, I gotcha. Cool. Alrighty. Have a good night, Superbrain. Have a good night, everybody else out there. And thank you so much for either watching the VOD or coming live or any of that stuff. If you want to come and find me, again, it's Obi-Wan Pez, and I am here at N Simplex Pachinko. So have a good night, everybody. See you on Friday for games. Probably going to do Manifold Garden again at some point. Yeah, I might need your help on Manifold Garden at some point. I got stuck, and I was like, where do I put this? Anyway, see you later.